Okay. So we're going to talk about one type of rhythm today, but there are, just so you know and you're aware, there are many different types of biological rhythms, which is basically fluctuations. It could be for food when the animal feels hungry, temperature, mood, and many different ones. So there's what's called circadian rhythms, and circ means about, dia means day. So circadian rhythms are the ones that are about repeating every day or every 24 hours. And that's the one that we're going to focus on beyond the slide, basically. There's also what's called ultra-radian rhythms. And this has to do with things that repeat more than once a day. So, for example, your temperature fluctuates, your ability to concentrate fluctuates, your feeding behaviors fluctuate, your hormones fluctuate. There's also what's called infradian rhythms, and this has to do with things that repeat less than once a day. So, for example, migration patterns in animals that happens once a year, body weight fluctuations, the menstrual cycle every 28 days. So these are just different types of rhythms, although we're going to focus on the first one. Okay. And then we have two types of animals, since we're going to be focusing on circadian rhythm, the one for wakefulness and sleep. Ones that are going to be sleeping during the nighttime and waking and being active during the day, and that's diurnal animals, so that would include us. Okay. Nocturnal animals are ones that are going to be active at nighttime and sleeping during the day. So these two types will have different circadian rhythms. And the circadian rhythms, how does the animal know? Is because they're going to have a biological, built-in biological clock. In the absence of light, okay, when there's no stimulus out there, no noise, no light, nothing to tell when is day and when is night, the animal develops what's called a free running cycle. And we call any two repeating points in the cycle a period. And how we typically study this, how long the animal sleeps, and how is that affected by by the presence or absence of stimuli out there in the environment, is by something like this. So animals like to go on wheels, like to exercise on wheels. I wish I did too, but rodents really like to do this. And in this paradigm, every revolution of this wheel will press something on the computer, so it will print a line, a black line, meaning that the animal was active. The absence of the black line would mean that the animal was sleeping. So then with this type of paradigm, it would tell me how long the animal slept, whether it was sleeping during nighttime, daytime, whether it was affected by some sort of lesion in a particular area in the brain, whether it was affected by the presence or the absence of a stimulus in the environment. Sometimes what happens if we trick the animal or human into maybe delaying the light a little bit is that their cycle will phase shift to entrain with this new rhythm. So for example, for humans, if I'm traveling to Canada, if I'm going east, it changes my rhythms because they're 3 hours ahead. So that change messes up my rhythms a little bit. And that jet lag makes you irritable and all that stuff. Okay. The light or that stimulus in the environment I'm talking about that kind of gives you clues about the time is what's called Zeitgeber. So here's what I'm talking about that comes out of the computer when we do that paradigm, when we implement the paradigm we talked about with the rodent. So all the black lines indicate that the animal was active, so on the wheel, revolutions of the wheel, and then all of the absence of it shows that the animal was not active. So when we provide a shift in time, so if I point your attention to this part right here by the phase shift, what happens is you get a phase shift. That the animal cycle shifts a little bit to entrain with the timing of the light. in constant dim light, so where the animal doesn't have any clues about the days at nighttime, the animal cycle gets messed up. And what it is generated is what's called a free running rhythm. Okay, so do we actually have a biological clock? Or is that just something, you know, for the media to talk about, for a magazine to write about? Do we actually have a biological clock? And it turns out that we do have a biological clock that's located in the suprachiasmatic nucleus. Does anybody remember what chiasm means? It means X. So it's basically out of each eye you have a bundle of axons that crisscross, so that's why it's called chiasm. And this is located right on top of that crisscross. Okay? Called the suprachiasmatic nucleus. We know that if we were to take the suprachiasmatic nucleus from the brain of an animal on a dish on its own, that it would tick, it would fire action potentials and rhythms that are in sync with the circadian rhythm of that animal on its own. Okay? Does that make sense? So let's see what happens if it is true that the suprachiasmatic nucleus is important for circadian rhythms. Well, what would happen if we take it out? If it's important, then the animal shouldn't have any circadian rhythms. So let's see what happens using the same paradigm I described earlier. So you have the normal circadian rhythms in the top part of the figure here, where the animal is active during the dark and sleeping during the light, because this is a nocturnal animal. You lesion the suprachiasmatic nucleus, and what happens to the rhythms? What's happening there? It gets scattered, exactly. It's almost random, sporadic, like they're active and then go to sleep. They're active a little bit, they go to sleep. It's not really in sync with the light and dark after the lesion. Okay? Although I want to say that predominantly they're still active much more during the dark than the light. But the lesion plus constant dim light, so they don't have the Zeitgeber, they don't have the light as a stimulus, and they also don't have the biological clock, you would truly get a very random, scattered, sleep wakefulness periods. Okay? If we look at a slice here showing the suprachiasmatic nucleus, so right on the bottom, these two circles here, that's the suprachiasmatic nucleus. When we look at the metabolic activity, as something that stands for the metabolic activity, we see that when the animal is during the light, you see that it's dark, it stains dark. When it's has lower metabolic rate, that it's light. So we know that this suprachiasmatic nucleus, yet another line of evidence showing that it is important for setting your rhythms, or it is your biological clock. Okay. Hamsters happen to have the same rhythms like humans. So they have 24-hour rhythms just like humans. Okay? So what we know is that there is this strain of hamsters that have a mutant gene that lets them sleep only 20 hours. Or that gives them a cycle of only 20 hours as opposed to 24. So what would happen if we transplant tissue from the hamsters that have the 20-hour rhythm cycle into hamsters that have irregular 24-hour cycle? What do you think would happen?
It flip out.
It what?
Flip out.
Okay. And how about when it stops and it gets accustomed to it and it stops flipping out? What happens?
The rhythm change.
In sync with what? The 24-hour or the 20-hour?
The 20, right?
The 20-hour. So the recipient will then have rhythms that are consistent with the donor. 20 hours. When we do the opposite happens. Again?
I was going to say it's almost like that hard thing, huh? Like when they put the
Yeah, the frog
heart.
experiment.
Yeah.
Okay? So our hypothesis again is that there is an endogenous, produced within, clock that ticks in sync with our circadian rhythms, and it's located in the suprachiasmatic nucleus. Okay? So what happens if we lesion the suprachiasmatic nucleus? Then we know that it's going to do, hopefully it'll do something to the circadian rhythms. Okay? So, and then again, if it is true that the suprachiasmatic nucleus is important for the circadian rhythm, then like Christina said, if we take tissue from hamsters that have this mutant gene that allows them to sleep only 20 hours and implant it in a donor hamster, a recipient hamster that has a regular 24-hour cycle, that their cycle will now become 20-hour rhythms. Okay? Again, showing yet another line of evidence that the suprachiasmatic nucleus is the biological clocks, and that any problems there is going to interfere with your biological circadian rhythms. Okay. Now, your circadian rhythms entrain to, they sync with, okay, the light-dark cycles. Now, you have a pineal gland, and I mentioned this briefly in one of the lectures, that in birds and amphibians, because their skull is so thin, the light can actually penetrate and activate the gland to release melatonin. In other words, the amphibians and birds, the pineal gland there is sensitive to light. In other words, it has photoreceptors, okay, that will secrete melatonin. In mammals, that doesn't quite happen, right? It's not like the light is going to penetrate through your skull and reset your circadian rhythms, right? So there has to be a different mechanism. So we know that from the back of the retina, okay, and we'll talk about what happened from the back of the retina in the visual chapter, the much more traditional pathway. This is the exception, okay, a very little branch of the, from the back of the retina will go to the hypothalamus. And there is specialized cells there that are called the retinal ganglion cells that are in the very back of the eye that will project straight to the suprachiasmatic nucleus, telling the suprachiasmatic nucleus about the light out there. Okay? So the back of the eye, the retina, has specialized neurons called ganglion cells that contain photoreceptors, meaning these specialized neurons that will take this light energy and transduce it or convert it to energy that the nervous system understands. Okay? We'll take that information and it will take it straight to the suprachiasmatic nucleus in the hypothalamus. That's why it's called retino-hypothalamic pathway, because it goes from the retina to the suprachiasmatic nucleus in the hypothalamus. Okay, and the pigment that's in that cell is called melanoopsin, because for the melatonin. And when we do the visual chapter, you'll see how every photoreceptor in the back of the eye has its own opsin or its own pigment. So we'll talk about that much more in details when we do that chapter. Okay, so here is kind of like a depiction of what I just said. The light hits the back of the eye, the retina. There's the traditional photoreceptors, the blue and the green. We're not going to worry about that till chapter 6. And then there's the untraditional ones, the ganglion cells, that will go straight to the suprachiasmatic nucleus. And also the light from the environment can reset or send feedback to the suprachiasmatic nucleus. For example, if you are traveling east and need to reset your biological clock. Does that make sense? Does anybody know what Drosophila means? Does anybody know what Phil means? Huh?
Like.
Phil, to what?
Like.
To like, exactly. To like or to love. Drosophila means liking or loving sweets, which is the fly. Okay, so the fly also is a diurnal or has diurnal circadian rhythms just like humans. So we can look at the molecular mechanisms for sleep by studying Drosophila and by creating mutations in Drosophila to see what happens and how it affects your sleep cycle. Why would you want to study sleep patterns and the molecular mechanisms of anything that pertains to humans and flies? Why would that be good? Especially when it comes to molecular and genetic stuff. Why would that be a good thing? Why would you want to study genes by looking at species like flies? How fast do flies multiply?
Very fast.
Very fast. And if you, huh?
They have short lives, right?
Exactly. So if you want to look at genetic variations and mutations and how it's inherited and how it has an effect on the next generation, flies offer the best type of species to study these types of things. Okay? And a lot of genetic molecular studies will use flies for that exact reason. Okay? So molecular studies in Drosophila, we can do a mutation, or what we found out is that you do a mutation in a gene called the period gene, and that does things to your circadian clock in mammals. So we know that they're related. Okay? We know also, as a result of the studies, the molecular studies in Drosophila, that the suprachiasmatic nucleus in mammals makes two proteins that are going to be crucial to setting and maintaining your circadian rhythms, and that is clock and cycle. And I just love the way they're named, because they're so telling of what they do. Okay. Now the next couple of slides are not going to be the easiest thing in the world to understand. Okay, but let's try to go through this together. So the clock and cycle proteins are going to bind together, what we call dimer. Di means two. Dimerize, so they're going to bind together. And when the clock and cycle dimer becomes one thing, it promotes the transcription of genes. So does anybody remember what transcription factors mean? Transcription factors? DNA, huh? Exactly, absolutely, yes. DNA to RNA, that's transcription. But what makes the DNA get to the RNA is the transcription factors. Okay? So the clock cycle dimer, when they dimerize, and only then it promotes the transcription of two genes, the period and the cryptochrome, the per and the cry. Okay? And the per and the cry, in turn, these proteins will also bind to each other, and they will bind to another protein called tau, which actually means time. Okay? Now this complex, this protein complex, the period, the cry, the tau, will then enter the nucleus and inhibit the transcription of themselves, of the per and the cry. Okay? So you don't make any more new proteins, no more period, no more cry genes, nothing of that until this complex is completely degenerated. And how long does this cycle take? 24 hours. Okay, so let's go through this again, but schematically, and see if it makes sense a little bit. Okay, so here's a picture. You have two proteins, clock and cycle, and only when the clock and cycle dimerize, they bind to each other. They then bind to DNA, function like transcription factors, so activating genes to produce other RNA, which then will make proteins. And what are the proteins that are made here? Period and cry, or per and cry. Okay, and once these proteins are made, the per and cry themselves would also dimerize, would also bind together, and they also bind to a third protein called tau. This protein complex here, only when bound together, they then activate or go in the nucleus to inhibit their own transcription, meaning making less of them. So we don't make any more of this clock cycle proteins unless the whole thing is degenerated. And this entire cycle takes 24 hours, and it's also under the regulation of input from the retina. So for example, if you're jet lagging, if there is a difference, something that resets your biological clock. Does that make sense? Okay, do we understand the molecular genetic basis, some of the proteins involved in this 24-hour cycle? So obviously anything wrong with any of these genes will affect your circadian rhythms. Okay. So what does this mean to us behaviorally? Okay. People who have a double clock mutation, So you know how you have one allele from the mother, one from the father. If both of them are mutants, both clock genes are mutants, they have severely arrhythmic circadian rhythms. Their circadian rhythm gets out of rhythm and it becomes arrhythmic. Does that make sense? And then also what we have found is that people who tend to be morning people, they're just much more effective, they're much more active, they're much more productive during the morning, early in the morning. They tend to have a different version of the clock gene than night owls. Okay? So there's actually a genetic basis to whether a person is going to be more active during the day or more of a person that likes to work late at night and is more productive at nighttime. Does that make sense? Yes, and then yes.
What if I'm like midday? Like I'm fine at night, I love the morning, but midday I'm exhausted no matter what I do.
Oh, but everybody gets that 3 o'clock, you know, lower blood sugar, tired, fatigue kind of thing. Everybody gets that.
But I mean, I'm perfectly fine at night. That's actually where I get my.
Oh yeah. So you're like a night owl then.
And morning, either or.
Okay, you're lucky. Okay, but typically people who are very early morning and they're very productive, like my mom is like that, so their genetic makeup might be a little bit different. Yes.
Couldn't it also be like a lifestyle? What's the word I'm looking for? Like if you have a certain lifestyle, that kind of changes how you get used to working at night. If you have a night shift.
Oh, we'll talk about the night shifts. I have a lot to say about that.
Okay.
Okay, but you're right though, that you're going to have stimuli. So if you remember in the picture that I had, I said this whole thing is under also, or gets influence and gets information from the back of the retina, from the back of the eye. Okay? So for example, light, now we have synthetic light, not daylight. That's going to prolong your circadian rhythm and make you stay up longer than before when we didn't have electricity, we didn't have light. When the lights are out, it's dark. Okay? But you're right, if you exercise at nighttime, that's going to interfere with your circadian rhythm. But someone who is a night owl to start with might not have a problem with working late night hours. It might not interfere with them as much as someone who is not like a night owl and doesn't have that genetic, you know, makeup that makes it easier for them.
So like even with repeated exposure, you can't like train yourself to be a night owl?
No. So you have circadian rhythms, a biological clock, and that biological clock has biological rhythms. And when you don't respect this biological rhythms, it's not good. And we'll talk about what happens when you actually sleep less hours per night than you're supposed to. What happens? We'll talk about that towards the end of the chapter. And I'm sorry.
And can people change their style from night owl to morning people? Can they do that?
Can they share?
Answer.
So what happens is that, just like I was saying, is that you have genetic predispositions to be a certain way. Okay, when you go against these genetic predispositions, you're not doing yourself a favor. Okay, it's best to go with your predispositions. Okay. Okay, we talked about sleep, just like actually a few of the comments that were just said, is going to be synchronized to external events, so that, for example, if the light is on longer, food, if you're eating late, alarm clocks, all that stuff is going to interfere, or it's going to affect your circadian rhythms. So what happens if we have humans live in a cave, where there's absolutely no light, no clocks, no show to let you know it's 11 o'clock, no cues about time whatsoever? What happens? Huh? Exactly, which is the free, well, they're going to start having free running rhythms, just like in the animals, and it's about 24 hours. Okay? So when they actually have done that, what they found was that in 77 days, that they slept what's worth, or what's equivalent to 74 nights. Does that make sense? Because they slept an hour, or the circadian rhythm was 1 hour extra. Because also our circadian rhythm is a little bit more than 24, not exactly 24. Okay, so what's happening to your brain when you're sleeping? What does the electrical activity look like? Okay, is the brain completely shut off when you're sleeping?
No.
Good. Okay, and how we know that is by looking at or recording an electro for electrical, and encephalo for head, graph for, because it gives you a graph on a computer sheet. So EEG, which records electrical activity in the brain, and also by recording electrical activity from eye movements, right by the eyes, you can have electrodes there. Okay, and doing that, we now know that there are two distinct broad categories of sleep. What's called slow wave sleep, okay, and we'll see what exactly that looks like. And under that, we're going to have 4 different stages. And rapid eye movement, where the EEG waves look very different from slow wave sleep. And also, your muscle and posture and motor activity is very different. Your brain will look very different. And in addition, the electrode right next to your eyes will give you different waveforms. So let's find out what's going on. Okay, so when the person is awake, their brain, the different parts of the brain are doing different things. Okay, and we call that it's desynchronized. So the waveform that we get, the EEG that we get, it's desynchronized. D means the undoing, synchronized meaning not like that it's in sync. So desynchronized because you're doing so many different things, the different brain parts will do different things. Therefore, the wave that you get is going to be desynchronized. Okay, and the frequency of that wave is typically 15 to 20 hertz. Hertz just means how many cycles per second. So this means 15 to 20 cycles per second. Okay, this type of frequency along with a very low amplitude is what we call beta activity. So beta activity is synonymous with desynchronized EEG. As the person relaxes or is extremely concentrating and is going into sleep, but not asleep yet, the frequency slows down from 15 to 20 hertz to 8 to 12 hertz. Okay. Nonetheless, the brain is still somewhat desynchronized. And here is what I mean by the frequency and the amplitude. So when the person is awake, what's called beta rhythms on top there, the very top. What do you notice about the amplitude of the waveform, the height of the waveform? Exactly. They're shorter, smaller, absolutely. What do you notice about the frequency? They're very frequent. Okay, that's what I mean by a desynchronized EEG. Okay? And then what do you notice as you go from stage 1 all the way to stage 3? So in B, C, D, and E. What do you notice? What's happening to the amplitude of the waveform? Exactly. It's getting larger, that's for sure, yes. And what's happening to the frequency? What? It's becoming more frequent or less frequent? Less frequent. So you get an amplitude that's much larger as you get in deeper and deeper sleep, and the frequency is reduced. Okay, and we'll talk about each of these stages. Okay. Now I just want to point your attention to F, REM sleep, and A. Do you see how similar they are? Okay, and we'll talk about what that means. Okay, so let's begin with stage 1. And I love how the stages are called stage 1, 2, 3. It's like so easy. So you won't make a mistake on the test if I say what comes first, stage 2 or stage 3. I hope not. You never know. Okay, so so we're going to begin with, remember I said there's 2 broad categories, the slow wave sleep and the REM sleep. So now we're only talking about the first one, the slow wave sleep. There's 4 different stages under that. The first one is going to show a regular frequency. And you're going to have the amplitude, a much smaller amplitude, just like you saw in the previous slide. Your heart rate slows, your muscle tension reduces, your eyes move more about, and this lasts about several minutes. So it looks kind of like this. You also get something that's indicative of stage 1 slow wave sleep, which is called vertex spikes, which is this. I mean, it looks like it doesn't belong in the waveform because of the larger amplitude and how it looks like it was superimposed in that waveform. And then you have stage 2. Stage 2, the frequency now we're at 12 to 14 hertz. And there's two kind of signs for stage 2. One is that you have what's called sleep spindles, where you have this very high frequency. You see that here? This high frequency? And then 2, you have what's called K complex, which is this sharp negative waveform. So these two indicate that the person is in stage 2, slow wave sleep. Then stage 3 is divided into early and late. Early stage 3, the sleep spindles continue just like in stage 2, but the amplitude of the waveform starts to get larger than in stage 2 and 1, and the frequency starts to slow down, indicating that the brain is becoming more and more synchronous. These larger amplitudes, slower waveform is what's called delta waves. And that's when the person is in deep sleep. That's how I used to remember delta waves. It starts with D, deep sleep starts with D. Okay? So here, the frequency slows so much that now it's 1 per second. That's really, really slow. Now, when 50% of the time, this waveform, you have more delta waves, we call it late slow wave sleep. When it's less than 50%, we call it early. When it's more, we call it late. Okay? So note the high amplitude, almost like stretched out a little bit. So just 1 every second. It's really low frequency. Okay? Does that make sense? Okay. So you have stages 1, 2, early 3, late 3, which is the slow wave sleep, which is about 1 hour. And then you return a little bit briefly to stage 2, and then something very interesting happens. And that is you get what's called rapid eye movement sleep, or REM sleep, where the EEG activations, just like you pointed out earlier, look very much as though the person is awake. Meaning the brain looks desynchronized, the amplitude of the waveform is shorter or smaller, and the frequency has high frequency waves. At the same time though, so we're eavesdropping on the brain, we see electrically it looks like you're awake, but if we were to measure your muscle tension, we'd see that all your larger muscles are paralyzed. Okay? And why do you think it's a good idea for your larger muscles to be paralyzed?
So you don't act out your dreams?
Exactly. In fact, people who have a genetic a mutation where that inhibition is there, they actually act out their dreams, which might be fun, but maybe not for the person when they wake up. Okay, so again, here's the EEG activity. It looks very much like the person is awake, and that's why sometimes we call it paradoxical sleep, because the person, when we look at the brain, it looks like it's very active, but the muscles are paralyzed. Yes?
Is that for sleepwalkers, or is that something totally different?
That's a little bit different. It's a little bit different. But we'll talk about sleepwalking too. Okay, so in a typical night, a person sleeps 7 to 8 hours. 45% to 50% of the 7 to 8 hours is spent in stage 2. Okay? 20% in REM sleep. And then obviously the rest is in deep sleep or stage 3. This whole cycle of all the different stages is about 90 to 110 minutes. Okay? But the distribution of the different 4 plus REM sleep stages are not uniform throughout the night. So at the beginning of the night, you have more deep sleep, more slow wave sleep, delta waves. And as the night wears off, you have more REM sleep. That's why it's much harder to wake you up in the middle of the night when you're going through slow wave sleep, and it's easier to wake up later on in the night because you're going through REM sleep. Okay? Does that make sense? Okay. And typically what I will tell someone who's like, okay, I don't have any time to sleep, and I say at least get 110 minutes of sleep so you can get all the stages in there. And you had a question?
Yeah, sometimes I wake up and I feel very tired and I don't want to do anything. And sometimes I wake up and I feel like healthy.
Very,
Healthy, yeah. So,
And under both conditions, you slept the same number of hours?
yeah.
Okay. So your level of arousal, ability to concentrate, and all that is going to fluctuate with, I mean, this is going to be important, of course, and your brain, as you'll learn later on in the lecture, keeps an account of sleep deprivation. So maybe the night before you slept your 8 hours or whatever that makes you feel rested, but maybe nights before that you were sleep deprived. The brain will actually keep an account of that. And also hormonal fluctuations. There's so many other factors that go in there. And as I said at the onset of the lecture, your arousal, attention also cycles. Okay, so it goes in waves as well. Okay, yeah. Stephanie.
Thing is sleeping too much, like over.
Yes, excessive sleeping is also not good for you. Yeah.
Do you think that a person, like, I have an instance where if I get 4 hours of sleep, I'm actually better off during the day as opposed to like 6 or 7? Do you think it's because I was trained to do that, or?
I mean, okay, so hold up to this question when we talk about the number of hours at nighttime and what they're related to, and some exceptions to that. I think, remind me of this question again later on. Okay, I promise we're going to address that. Okay, so let's contrast, and this is an extremely important table, so like when you're studying this in the PowerPoints, you really need to know this. Slow wave sleep versus REM sleep. So your autonomic nervous system activity, the heart rate for slow wave slows down, you breathe slower, your brain temperature decreases, and that's why when you're going to sleep at the beginning of the night, you want to be covered. You feel your temperature actually decreases. Your blood flow to the brain also is reduced, as opposed to REM sleep, where your heart rate will fluctuate. So, and if you have a little child, you actually can see how the heart rate, their breathing rate is fluctuating. Like it will fluctuate, and it's very obvious with an infant or a child. Okay, your brain temperature increases. So as the night wears off and as you wake up, you get hot, and that's because your temperature is increasing. The blood flow to the brain also increases or is high, and that's because we dream during this stage. Okay, your muscles, your posture is progressively reduced, but it's completely eliminated. You're paralyzed during REM sleep. Okay. Your knee-jerk reaction is completely normal, but if you're going through REM sleep, it's suppressed. Okay, so if you go like this to their knees, they don't actually do this reflex. Okay, I know all of you are going to try this on your partners when you go home, and if they randomly wake up as you hit their knees, I'm not responsible for that. Okay. Twitches. So although the large muscles are paralyzed during REM sleep, that you do get twitches during REM sleep as well, but you don't get them so much during slow wave sleep. Eye movement during slow wave sleep are really not there, but during REM sleep you get this rapid eye movement every minute and a half or so, and it's very obvious in children. So if someone says, well, I never dream, then wait for them when they're sleeping, wait till their eyes, they show the rapid eye movement and this profile of autonomic nervous system, and wake them up. And tell me what they say and ask them, were you dreaming or not? Okay? Don't try this at home. Yeah.
So how does this work on people who are light sleepers? Do they still go through this, or?
Yeah. Yeah. But there's the genetic differences to some people, you're right, are light sleepers, and also age. So later on in the lecture, we'll look at age and how it affects the different stages, and why then as we age, we become light sleepers. Okay? Okay, cognitive state, really, when you slow wave sleep, there isn't really much of that, but when you're in REM sleep, you do get cognition, you do have vivid dreams that are well organized, you do go through emotions. Hormonal release, very low in REM sleep, but during slow wave sleep, you get a release of, high release of growth hormones. And that's why children who are sleep deprived and who don't get to experience a lot of slow wave sleep, they don't grow. And also, as you will find out later in the chapter, that as we age, we get less of the slow wave sleep, meaning less growth hormones, which is going to have effects on us as we age. And we'll talk about that later. Yeah.
What about people that like talk in their sleep? Because I totally talk in my sleep, and you can.
I loved it. My sister used to do that. I loved it because I want to find out.
Yeah, I know. It's awful. People can like ask me questions, and I have no recognition of like actually telling them like the answers.
Well,
and
even though we've wait. Okay, one second. Okay, so before I answer that, so here's the distribution of the different stages across 8 hours of sleep. The width of each bar tells you how long you stay in that stage. So if you see at the beginning of the night the purple bars, okay, they're more narrow, but as the night wears off, what happens? They become wider, meaning that you're spending more time in REM sleep. And what do you have with many of these REM sleeps? You have also what's called brief awakening. So you actually wake up throughout the night. But how come you don't remember that you woke up all these different times?
Because with the sleep right after.
Yeah, and you never remember how you fell asleep or how long it took you to fall asleep. So I don't know if you did this when you were young, but I remember as a child I was always like, okay, today's the night where I'm going to track how I fell asleep. Oh, yeah, you did that too, right? Okay, good. I'm not like some weird child. Okay. And it's like you will never, ever, ever remember because you never remember how you fell asleep. So if you have something to say to somebody that's not very pleasant, if you get them right when they're falling asleep, they won't remember a thing the next day. You got it out of your system, they won't remember a thing, it's done. Okay? So anyway, so that's why, back to your question, that's why you don't remember what you've said to them or what you said, because even though you might have brief awakenings where you're responding back to them, you don't remember because it was right before you went back to sleep again. Okay. So when at puberty, what happens is that people shift their circadian rhythms so that they need to wake up earlier. They need to wake up later. Okay? So it's actually better for high schools to have a later start hour for teenagers than an earlier one because they're much more productive later on in the morning than very early in the morning. If you want to make sure they underperform, you have a class for them at 7 or 6 o'clock in the morning. That will for surely make them underperform. Okay? And I know there are some schools, a few schools that have implemented a later start of the day for adolescents, and they tend to perform much better than when you force them to come very early in the day. Okay? So here is the age. We have on the x-axis the age in years. On the y, we have the type of person, late risers versus early risers. And the red is for females, the blue is for males. What you see is where does that peak, meaning it's closer to waking up much later. Where does it peak? Yeah, so about adolescence. And that peak is much bigger for boys than for girls. So you see there, it's right up there where late risers are. Okay, meaning teenage boys are just going to need to be sleepyheads for a while. Okay, but look at this. For earlier on, like age 8, 10, they tend to be very early risers. And anyone who has kids knows exactly what I'm talking about. Okay, so I see a lot of you nodding. So Adam, no matter what time he goes at nighttime, he's 8 now, but he's been doing this since he was born. He will wake up at 6 o'clock. He used to wake up at 5 something every day. Okay, like it's like, Adam, it's still dark outside. You need to go back to sleep. It's still in the middle of the night. He will wake up at the same time at 6 or before 6 every day. Meanwhile, my daughter, Yara, who's now 10, she will sleep in a lot more. Okay? And she doesn't like to wake up early. Okay? So I definitely see these differences at home. And then I know from my friends who have boys who are older that as he enters adolescence or becomes a preteen, that he's going to need to sleep in more. So I'm desperately waiting for that to happen. Okay. All right. So vivid dreams, or the dreams as you know them, happen in what's called REM sleep, okay, where there's that sense that the dreamer is actually there. And sometimes you get the sense that you are actually directing the dream. Like, I want this to happen next, so it happens. Yes?
Oh, I was going to ask about that actually. I heard that lucid dreaming actually disrupts your REM sleep. Is that true?
I don't think it does. I don't think it does. There's actually certain types of therapies that train you to do lucid dreaming. So that will implement things to know when you're in REM sleep, and will kind of give you a signal so you can actually lucid dream. Okay. Anyways, okay, so this is very different than night terrors. So nightmares, obviously, that's frightening, and it might wake you up from your REM sleep, and you get the autonomic heart rate and all that with it. But the night terrors that happens in children, which are frequent, although they're night terrors and it terrifies the parents, they're not terrifying to the child because they don't remember anything the next day. Okay, it's not like they're scared by the nightmare that they had. And night terrors, unlike dreams, happen during stage 3, slow wave sleep, unlike REM sleep. And they typically happen during the early part of the evening. Okay, much less during the latter part of the evening. Okay, do animals dream? Okay, we know that nearly all mammals show both REM sleep and slow wave sleep. Okay, but rabbits, bunnies, they show both types of stages. But sometimes what they do, they're very light sleepers. Rabbits are very light sleepers, and sometimes they trick you because both their eyes are open, and you think they're not sleeping, but they're sleeping. Okay, but think about it. They're like little cute mammals that are so cute, and everybody wants to eat them, including humans. Some people eat rabbits. So like they have to protect themselves. Okay, and they tend to be really light sleepers. Okay, how about other types of animals? Okay, for example, vertebrates. What happens to them? And everybody knows what I mean by vertebrates. So animals that have a backbone. So vertebrates and birds display some vertebrates, anyways, will display both REM and slow wave sleep. But how about very big animals like dolphins and seals? They're in the water. They have to go and get air and oxygen. So if they go through REM sleep, what happens to their muscles? They're paralyzed. So can they do that? No. They can't do that. Okay, but what they can do is that they'll sleep. They'll go through slow wave sleep, not REM sleep. But, and what do you want to say?
Yeah, they sleep only half.
Exactly. They sleep only one half a brain at a time. So one hemisphere will go to sleep, then the other hemisphere will go to sleep. If you think that's cool, birds can do the same thing, because they're flying, and they sometimes will fly like 12,000 miles. I forgot what that bird is called. So it actually sees 2 summers a year. It actually will go through 2 summers a year. So what is it going to do? So it'll go through REM sleep and slow wave sleep, and it can only do the unilateral sleep, where only one hemisphere goes on at a time, but it can actually control that. So it can control whether it's one hemisphere that goes to sleep or both hemispheres that go to sleep, depending on how risky the situation is. And it can also sleep with one eye open. So flying, sleeping with one eye open, one hemisphere at a time.
There's nothing up there for them to hit.
Okay, and it was birds take like hundreds of second naps throughout the day. Okay, because one unilateral slow wave sleep is not as good as when the entire brain shuts down, which they can do, which is like remarkable that they can actually control whether one hemisphere goes to sleep or 2. When they're not in a risky situation, they will be able to do that. Yeah.
All right, I'm gonna try to word this where it's not like soldiers that are trained to like stay alert. Is there like our brain doing something similar? Not like.
So it's funny that you say that.
Good.
Because I don't know what the science on it is, and if it is scientifically, if there is science to it, I couldn't see anything on that. But there have been anecdotal stories of veterans under severe stress sleeping one hemisphere at a time and with one eye open. Okay, But again, these are anecdotes. I don't know how true they are. They seem believable given how your body and brain can function under severe stress. But we don't know for sure. We haven't shown it like in a lab. We haven't shown it, with scientific rigor. Okay, does that make sense? Okay, talked about dolphins. Okay, let me show you what this unilateral sleep looks like if we're recording electrical activity. So the top panel is the right hemisphere. The bottom is the left hemisphere. When we're awake, the brain is desynchronized, or in stage 1, the brain is pretty much desynchronized. As the person goes in slow wave sleep, stage 3, the brain becomes synchronized. In humans and animals that are not at risk, both hemispheres will go to sleep at the same time. Both hemispheres will show delta waves at the same time. For dolphins, what you see here is that the right hemisphere shows synchronization, delta waves. The left hemisphere is showing waveform that's very consistent with being awake, or stage 1. You see that? And then it switches, okay, where this hemisphere, the right hemisphere now is showing waveform that's very low in amplitude, that's more frequent, and then the left hemisphere now gets to go through delta sleep wave where they can go into deep sleep. Okay, does that make sense? Any questions on that? Okay, now back to somebody's question over there. Mammals will sleep more during infancy than as we get older. Okay, and anyone who has infants or who has kids know this. And they also, although they sleep many hours, they're not able to maintain many consecutive hours. So any parent knows that the first year they have to wake up multiple times, and then the infant is just going to they're going to sleep for a little bit, they're going to wake up. They're going to sleep for a little bit, they're going to wake up. That is a sign of the brain being still immature. And actually, as the child learns to sleep throughout the night, consecutive hours, that's a sign of the brain maturing. Okay. Now, if a child is a year old and is still not able to do consecutive hours, then something is wrong. Okay. So the black or the dark portions indicate the time sleep. The blank parts are when they're awake. On the y-axis, if you will, that's weeks after birth. So it's basically the age of the infant. And on the bottom here, you have time. So what you see when they're first born at 3, 4, 5, 6 weeks, at the very beginning, you see that pretty much it's scattered. They sleep a little bit, they wake up. They sleep a little bit, they wake up. And at about 16 weeks or so, they start to sleep longer and longer periods of time. Okay? So some of my friends think I'm a little bit cruel because at 6 months, I have my children sleep in their own bedroom, and I shut the door, and that's it. They're gone for the night. I will not, unless they need to be fed, once maybe throughout the night, but I expect them to sleep consecutively throughout, for a few hours, 4 to 6 hours at a time. And I won't go in if they're crying. They can cry for as long as they want. I won't go in, which is very difficult for my mother-in-law when she was visiting to deal with, because she thought I was torturing my daughter, but she went to sleep eventually. Okay. Also, the distribution of the different stages will also change. So when the infant is born, what you have is that most or a big percentage of sleep is REM sleep. They spent a lot more time in REM sleep than in slow wave sleep. But as we get older, we spend less time in REM sleep and more time in other non-REM sleep. Stages 1, 2, 3, and 4. Okay? In fact, so remember how I said like they spend about 50% of their time in REM sleep. In fact, if a baby is born prematurely, they can spend up to 80% of their sleep in REM sleep. Okay? So I'm sorry to say to all the parents who think they have the cutest baby because they're smiling all the time when they're sleeping, it's not that your baby is just exceptionally happy. All babies do that, and it's because they're going through REM sleep most of the night, and they're dreaming, and it's making them have these facial expressions, and they're smiling. Sorry. Okay. So as we age, we spend less total time in sleep, and we also, but the biggest loss as we age is in stage 3. So as we age, we spend less and less and less time in stage 3. Okay? So at age 60, we spent half as much time as when we were 20 in stage 3. At 90, stage 3 is completely gone. Okay? Now remember that it's during this stage that growth hormone is being released. Okay? So we know that the disappearance or the reduction in stage 3 is also related to a decrement in cognition. And that people who suffer from dementias or cognitive problems, that is also related to a reduction in stage 3. That's beyond normal. Okay? Do you have a question?
My great grandma, she's 96. She's constantly sleeping, so she's just in.
Really?
Yeah.
That is very, very unlike like the average 96-year-old.
Well, I think it's because she kind of wants to die. It's horrible.
Oh.
It's horrible, but she, yeah.
But how does she maintain a sleep? Because usually older people, they sleep less hours.
Yeah, that's why I'm confused. She's constantly napping. She sleeps through the night. It's just strange.
Well, lucky for you guys, I guess. Yeah, that's bizarre. That's very bizarre. And is she sick or anything? Is she no?
She's healthy.
She's healthy. Oh, okay, that's really good. Yeah, that would be interesting to see what the quality of the sleep is like. You know, if she does go still through stage 3 or not. That would be very interesting to find out. Okay, so here is one for older, 60 years of age or older. As you can see, the blue dashed arrows there pointing at stage 3, showing narrower bars for stage 3 or less and less time spent in stage 3. And more time or more frequent occurrence of what? Of what? Of what? I can't hear you. Exactly. Of waking up throughout the night. And that's why it's very difficult to sneak in when you live with your grandmother or your grandfather, and I see some of you are nodding, because they don't really have a deep sleep, and they have these frequent, they wake up very frequently throughout the night. So they're very light sleepers. Okay? Now, I don't want to paint like a negative view of this. I actually see this as something that's really good. I actually see the fact that as we age, and you're 60 now, you have less responsibilities, you've already done the kids thing, the career thing, I think it's a good idea that you dilate the moment, you dilate time, you increase the time available where you're awake to enjoy life a little bit. That time was a luxury beyond that point, and now you have this luxury to read, to do things that you weren't able to do before. And also, I see it as positive because you're getting closer to death as you age, yeah? So I think dilating the day or having more time during the day to be awake, that just like makes more hours available for you before you die. But so I see it a bit more positively than it seems here, okay? All right. And then so somebody in the back asked about the sleep deprivation, okay? So what happens when we don't sleep enough? Okay. And you probably have experienced that if you're studying up all night or something for a test. The next day you're very irritable. You have difficulty concentrating. So it's the worst thing to do is to stay up all night studying for an exam and then come to do an exam that requires conceptually or some sort of creative answers. You won't do well on that. Okay? And then also you might go through episodes of disorientation. Like I don't know if that's ever happened to you, where like you're doing the same thing you've done before, like maybe driving in a familiar area, and yet you just feel disoriented for a second. We're like, wait, I've never seen this along the freeway before. Where am I? Has anyone gone through that before? So that can happen when you don't get enough hours of sleep. You get this disorienting kind of episodes throughout the day. And then also your immune system suffers. And that's why if you pull all-nighters during the final exam week, and you're like, oh, do I have to get the flu this week? Does it have to happen when I have exams? And it's because you're not getting enough sleep, your immune system is weak, so you're more likely to get anything that's out there. Okay? And it's related to so many, many, many other things. So for example, it's also related to impotency and infertility. Okay, so with 1 every 6 couples in America being infertile, this might have something to do with it. Okay? And then these factors are exacerbated as we age as well. Yes?
I also heard that sleep deprivation will make you gain weight.
Yes. Yeah. And even if it's for the simplest reasons of you are awake more hours to eat. Which totally happens to me because my kids go to sleep between 8 and 9. And then when they're sleeping, that's the time for me to sit down. And it's my time with the fridge. Okay?